Welcome back to another explainer. I'm absolutely thrilled to have you here today because, honestly, we're looking at a true paradigm shift in artificial intelligence. We're finally moving way beyond those language models that just chat with us, and we're stepping right into the wild realm of physical AI. Today, we're unpacking a groundbreaking new model called PHIZERO. And let me tell you, this isn't just another AI that spits out pretty aesthetic clips. No, this is an AI that has literally been taught to abstract raw visual data into a discrete physical language, so it can genuinely understand the fundamental dynamics of our physical world. It's a real game changer. So here's our master blueprint for how we're going to teach AI about the physical world today. We'll start by checking out the AI physics problem, then we'll define exactly what physical language is. From there, we'll unpack this amazing reason first, render later paradigm, take a peek under the hood at the tokenizer and reasoner, put the whole thing to the test against benchmarks, and finally, look at what the future holds for physical AI. All right, Section 1, the AI physics problem. Let's look at where current models are falling short. Okay, let's dive right into this with a totally brilliant quote from Sherlock Holmes that honestly just hits the nail on the head regarding the current state of video world models. Holmes says, "You see, but you do not observe." Right now, mainstream video AI models are basically trained by predicting direct pixels. They look at a frame and they just kind of guess what the next frame's pixel should look like. So they see the visual fidelity, sure, but they aren't actually observing the underlying rules of physics making those pixels move. Because all those underlying physical dynamics are left completely implicit inside this massive, messy soup of high-dimensional visual data, the models end up hallucinating physics. I mean, we've all seen it, right? Objects morphing randomly, things passing straight through each other. The physics just completely breaks down. Well, human intelligence works totally differently than that. We don't just walk around memorizing millions of visual outcomes. We naturally abstract patterns from what we see into generalizable rules about how things actually evolve. We organize this knowledge using language, and that gives us a symbolic space to explicitly reason about our environment. But here's the catch. When it comes to the highly complex state transitions of the physical world, natural spoken language it's way too coarse. You really can't easily describe the exact mathematically precise fluid dynamics of a water splash using everyday English words. We need something so much better. Moving on to Section 2. What is physical language? Let's define this finer-grained model.
So the crucial point here is that the researchers behind PHIZERO asked a pretty radical question. Can we learn a finer-grained representation of physical world transitions? And spoiler alert, they actually did. They developed what they call physical language. Basically, this is a compact, discrete representation of world state transitions. And the coolest part is that the model learns it entirely through self-supervision from countless unlabeled in-the-wild videos. It acts as an intermediate representation. The AI can explicitly reason about how the world is going to evolve using this new language, long before it ever attempts to draw even a single pixel on your screen.
To really help visualize this totally invisible concept, let's break down a super simple physical transition. Imagine pouring a glass of wine. Notice this initial state right here. We have a bottle tilted over a glass. The liquid is just breaching the very edge of the bottleneck. In a traditional model, the AI would just scramble to try and guess the next batch of red and brown pixels. But as we move into the actual transition phase, physics is now in active motion. A physical language model isn't just frantically memorizing pixels. It's capturing the actual real-world fluid dynamics. It's capturing the continuous state change, the flow rate of the liquid, the gravity pulling it down into the glass. It explicitly encodes this very specific physical action into a tight sequence of discrete tokens. And finally, we hit the consequence, the final state. The physical language actually provides a mathematical bridge connecting the very beginning of the sequence all the way to the end. By successfully disentangling the actual world dynamics from the superficial visual appearance, the model understands the true cause and the effect. And it does this without getting distracted by visual noise, things like the ambient lighting, the busy background, or the exact curvature of the wine glass. Which brings us to Section 3, reason first, render later. Let's look at this entirely new paradigm. Now, what's really interesting about this slide is how comprehensively it maps out the entire PHIZERO pipeline. It's like a giant puzzle coming together. If you look at the top left, we see the traditional human approach, right? Extracting abstract transitions from our visual experiences and then using language reasoning to understand them. Right next to it is PHIZERO's approach. It absorbs a ton of in-the-wild videos, pushes them straight through a tokenizer to learn this discrete physical language, and then uses a reasoner and a generator to output future video. But look at the bottom section. The downstream applications here are absolutely incredible.
On the far left, we've got general video world modeling, which shows physically realistic generation of complex things like coffee pouring or actual ocean waves crashing. In the middle, there's fine-grained world simulation. Here, the model accurately simulates an action-conditioned driving environment. It's actually predicting exactly how the environment shifts based on a car's specific steering input, or even how a robotic arm interacts with objects on a table. And over on the right, zero-shot motion transfer. This is wild. It literally takes the physical language of a human hand moving an object, and it transfers that exact physical logic onto a robotic hand, or a humanoid robot. It maintains perfect, flawless physical coherence across completely different visual domains. Distilling that massive pipeline down, it fundamentally operates on a very strict reason, then render paradigm. Step 1. The reasoner infers the future world evolution purely in the physical language space. It literally solves the complicated math of the physics first. Then, step 2, the diffusion decoder takes those securely inferred transitions and renders them into high-fidelity video. So, dynamics inference and pixel-level synthesis are completely, 100% separated.
Section 4. Tokenizer and reasoner explained. Time to look under the hood.
All right, let's dive deep into the core architecture here. This is exactly how the magic happens. First up is the physical language tokenizer. It takes a raw input video and uses something the researchers call a transition-level Q-former. Think of this component like an ultra-efficient zip file for physics. It brilliantly compresses all the complex, messy state transitions from that video into a highly compact, perfectly discrete physical language. Then we move over to the physical language reasoner. This is the engine for generating totally new scenarios. It utilizes an autoregressive vision language model, or VLM. You feed this VLM a first frame, which establishes the current state, along with a text prompt, like an action intent. Because the VLM already possesses rich visual semantics and basic common sense knowledge, it can accurately predict a brand new physical language sequence. It is effectively writing the mathematical script for how the physics will unfold. Finally, the diffusion decoder takes that script, anchors it securely to the static background of that very first frame, and reconstructs the future video, frame by frame.
And this brilliantly illustrates just how insanely efficient this tokenizer really is. The research team compared their tokenizer against a state-of-the-art continuous model called WEN 2.2 VAE. To put this into perspective, to reconstruct just 4 seconds of video, the continuous model required an immense 44,800 continuous visual tokens. That's huge! PHIZERO, on the other hand, it represented the exact same future state transitions with only 256 discrete physical language symbols. That is a staggering, almost unbelievable level of data compression. It proves beyond a shadow of a doubt that physical language successfully strips away all the redundant appearance information and focuses strictly on the pure underlying state changes. So once the model has those 256 highly compressed discrete tokens, it's time to actually render the video. The diffusion decoder starts with static noise and uses its pre-trained generative prior to build the image back up. Now, because the very first frame already provides the static scene appearance, the color of the walls, the shape of the table, the lighting, the decoder doesn't have to waste any computational time figuring that stuff out again. It uses the physical language tokens strictly to render the fine-grained visual details of the state transition itself. It pushes right through the noise to reveal a perfectly coherent consequence. Let's move to Section 5, putting it to the test. How does this actually stack up against benchmarks? Well, in a word, dominantly. PHIZERO was tested across some incredibly rigorous scientific generation benchmarks. On Physics IQ Verified, which directly compares generated AI videos to real physical rules, it achieved the highest IQ score out there. On PhysiGround, which is strictly judged by physics-specialized VLMs, it completely secured the best physics score. And on World Model Bench, it snagged the top score for physics adherence. It consistently, repeatedly outperforms the baselines, proving once and for all it doesn't just make pretty pictures, it generates truly physically coherent world evolution.
But let's step back. What do all those high scores actually mean in reality? It means that when you prompt PHIZERO with highly complex real-world interactions, it actually gets them right. If a heavy ball hits a pile of wooden blocks, the AI accurately models the realistic collision displacement. It genuinely understands gravity-driven deformation if a soft, squishy object falls to the ground. It can map out highly intricate chain reactions, and remarkably, it even accurately renders dynamically changing shadows as objects rotate around a static light source. It truly understands the fundamental consequences of complex physical interactions. Finally, Section 6, the future of physical AI. Let's look at the tangible impacts. Let's move to and see how this incredible reasoning translates into actual world-changing applications. Because PHIZERO rigorously separates reasoning from rendering, we can now exercise unprecedented, precise control over state evolution. For self-driving cars, this means we can create simulations that accurately follow extremely fine-grained driving trajectories, adapting to different steering magnitudes based on sequential control inputs. In the world of robotics, it means an AI that understands exactly how to execute a hyper-precise gripper movement to manipulate an object, simply because it inherently grasps the real-world physics of the interaction. It even opens the door for fully interactive world modeling, where a user can change camera viewpoints and positions on the fly while maintaining absolute, perfect temporal consistency.
It truly makes you wonder, doesn't it? We have spent years, literally years, training AI to be these incredible digital mimics, painting pictures pixel by beautiful pixel based on massive datasets. But PHIZERO represents a massive leap from just mimicking reality to fundamentally understanding it. By abstracting the complex physical world into a discrete language, we are finally giving AI the actual tools to reason about cause, effect, and consequence. So I want to leave you with this one final thought. What becomes possible when AI finally stops mimicking pixels and truly starts understanding the fundamental laws of our physical reality? Thank you so much for joining me on this explainer today. Keep learning, stay curious, and I'll catch you next time.